A modern robotic assembly line runs with incredible speed and precision, right up until a screen freezes and the entire operation grinds to a halt. This diagram shows the chain of command. The HMI acts as a vital bridge, translating physical operator commands into digital instructions for the PLC, driving the physical machinery. When that communication link breaks, production drops to zero. Guessing at the root cause inflates maintenance costs. Before taking apart the hardware, you need your baseline tools: a digital multimeter, spare communication cables, access to network configurations, and recent software backups. Systematically isolating faults is faster than guessing. By following a strict 7-step diagnostic workflow, you can rapidly pinpoint hardware, network, and software errors, getting the machinery back online efficiently. This 7-step flowchart guides our diagnostics. We start at the physical hardware level. Step 1 is checking the power supply. If the screen is completely blank, take out your multimeter. Test the input voltage at the terminals and test internal fuses for continuity. Locating a blown fuse or a loose wire here is a quick fix. Restoring the correct supply voltage will immediately trigger the system's boot sequence. If the device powers on but drops its network connection, we move to step 2, inspecting the communication cables. You have to get hands-on. Manually wiggle and reseat the Ethernet or serial cables at both the screen and the controller to detect loose connectors or areas exposed to severe electrical interference. A simple visual scan rarely reveals internal wire damage. If a cable looks pinched or strained, swap it with a known working spare immediately to eliminate intermittent physical faults. Securing power and cabling clears out erratic phantom hardware errors. With the physical layer confirmed stable, we can safely investigate the logical connections. Step 3 shifts our attention to the external brain of the machine, verifying the PLC status. Sometimes an inactive alarm screen or a frozen value is caused by the controller itself halting. Physically inspect the front panel of the PLC to confirm it is actively in run mode. If the PLC is running perfectly, but the interface remains disconnected, proceed to step 4. Testing the internal network settings. You must verify the interface's IP address, subnet mask, and target PLC address identically match the controller's network parameters. But communication is only half the battle. To display correct data, internal variables must map to precise PLC memory addresses. Aligning the IP addresses and the tag databases ensures the interface is pulling the exact right data from the exact right source. Once the hardware and logic layers are clear, we look for internal software bugs. Step 5 is reviewing internal alarms and diagnostics. If a specific feature, like a trend screen, fails to update, opening these diagnostic menus to check data logging parameters and adjust the sampling interval will usually fix the graph. For generalized sluggish performance or a touchscreen that fails to register commands, we implement Step 6, restart and optimize. Executing a soft reset clears out heavy background graphic loads. Once rebooted, recalibrating the touch matrix will ensure operator inputs register accurately. If the operating system remains locked or the databases are entirely corrupted, we proceed to our last resort, Step 7, restore backup. This involves flashing the firmware or uploading a known good configuration file, wiping out the corruption and forcing the unit back to a clean, stable baseline. Exhausting the internal diagnostics and soft resets first protects the current machine configuration. You only execute a hard restore when every other software fix fails. Reactive troubleshooting restores production today. Proactive maintenance ensures it stays running tomorrow. Long-term reliability requires strict habits, scheduling automated software backups, enforcing routine firmware updates, and maintaining physical enclosures to block dust, heat, and moisture. A highly automated manufacturing floor operates continuously because these strict maintenance protocols eliminate the friction of unexpected component failure. As we implement Industry 4.0 concepts, these local screens are transitioning into cloud-connected systems equipped with AI-assisted diagnostics to flag potential failures before operators even notice an issue. Mastering the physical, logical, and software troubleshooting layers today gives you the exact technical foundation required to manage the predictive, highly integrated smart systems of the future. Applying a 7-step diagnostic workflow clears out the variables, allowing you to quickly isolate faults and restore production. When you need expert support implementing these advanced problem-solving strategies, turn to DEVI Automation Solutions. DEVI provides comprehensive industrial engineering, specializing in PLC programming, complex SCADA systems, AI integration, and smart agriculture applications. Like and subscribe for more insights into industrial automation, and contact DEVI Automation Solutions to build powerful, reliable systems for a better tomorrow.